Hello, everyone. So today, let me bring you this very exciting results about extracting vital signs waveforms from, moving bodies. So this, we believe, has never been done before, at least not fully been done before. So I'm just representing four of our collaborators to present this work. So I guess everyone understands the importance of vital signs to be the indicator of both physical and mental status. So that's the reason we have a lot of devices made for this purpose. However, most of these devices are made for wearable. So they cause inconvenience and mostly cannot constantly monitoring the vital signs. So that's the reason many people are searching for contact-free monitoring methods as an alternative. So in which we believe that radio frequency sensing seems to be the ultimate answer because the fine granularity in sensing it provides. However, there is a robustness problem because body cannot remain constantly static. So we have to, kind of mask these body emotions in order to extract vital signs. For example, if we look at the right-hand side, when people are sitting statically, the RF sensing can recover the both breath and heartbeat very accurately. But if the subject is moving or walking on the treadmill, so we can see that sensory results can be totally damaged or at least made very inaccurate compared with the ground truth. So although many people have been using Wi-Fi for monitoring vital signs, but we believe that the commodity radars are better in this sense. So although there are two types of radars, IR-UWB for microwave and FMCW for millimeter wave, so they're actually very similar in their working principles. So we're just focusing on IR-UWB to introduce the basic idea. Because they're just time frequency duals, so the time CR for IRUWB will be equivalent to the FMCW CSI. So if we look at this matrix, in the fast time dimension, so when after a pulse is sent, then the kind of reflections will indicate how many subjects are out there given sufficient resolution, time resolution. And then if we look at different frames across the so-called slow time, then this moving or the shifting of the reflected pulses are showing the motions. For example, in this case, probably they're indicating the breath. But the problem is that this is a very ideal case where we assume that only one body motion exists, but there are a lot of them actually in reality. So we need to find an efficient way to actually separate them to extract the vital signs, which might be the weakest motion out of all these body motions. And to give you a better illustration, so we use the signals IQ space to better show how this RF sensing results look like. But here is, again, ideal case because when we sense the heart beat, we actually ask the subject to hold the breath. So we see that using the breath, we can see that in the perfect scenario, so the breath will showing a kind of circle shape, especially in the FMCW radar. But for the heartbeat, it becomes part of the circle, which is the arc. And so we also believe that it's better to look at this 2D space. If we just look at a single dimension, either the amplitude or the phase, since might not be so accurate, the sense signal might not be so accurately characterizing the vital signs. However, for UWB radars, the amplitude seems to be very close to the 2D sensing results, while the FMCW has its phase to be better. So this this results are not presented in the current paper, but you can find it in our MobiCom paper this year. So basically, the idea here is that we can see what kind of sensing results would be there in ideal case, but we also alert the reader and the audience that when we actually do the RF sensing, many of these motions, including these two, are mixed together. So how to extract or remove body movements and extract the vital signs, that's not very straightforward, although many have tried before. So either they recommend suspend sensing during body movements, but that's not a sustainable solution because we can't actually prevent the body from moving constantly. And others will suggest using collaborative radar sensing, so a multiple time synchronized radar to sense body movement and cancel them out. But the setting is so cumbersome, this has been long discarded. So the latest proposal use so-called, empirical or variational motion mode decomposition. To decompose all these motion patterns, including some of our latest work. But in the previous, the slides, the MobiCom paper actually shows that they failed in many circumstances. So recently we also have another low-end solution that aims to extract respiration out of body movements, which was published in Census last year. But so the current method we're discussing now is a high-end one, which simultaneously recovered two vital signs out of the many different type of body motions. So, and our sensing is conducted mostly on our IRUWB platform, which is named Octopus and will be presented next in this session. So now with all those incentives and the motivations being introduced, we can dive into the technical details. But before going to real details, we have to figure out, so what is this setting for our measurement? Firstly, we have to require the subject to face the radar, otherwise all the features will not be seen by the radar. The same thing applies to the FOV. So if the subject doesn't sit or stand within the FOV, so the radar can't see it either. And last but not least, we can't allow for the current method. It doesn't allow the subject to move drastically. So what we're requiring is that there's no big variations between the radar and subject distance. But we're working on a method to eliminate this constraint. So we also look at different body movements interference to the vital signs. So we see that we consider 3 movements against 1 static scenarios. And the backgrounds are the sensing matrix, as we explained earlier, and we actually use their magnitude to show the signal, to visualize the signal better. We can see that when the body remains relatively static, the vital signs are pretty obvious, but they are kind of totally annihilated, when some body motion are involved. And within the body motion, we also have different types. For example, the plane phones are kind of purely random. We call them stationary. And similarly, the treadmill is also stationary, but there is some kind of periodical pattern, so we call it cyclostationary, but both are kind of within the stationary category. There are also non-stationary movements, which are kind of temporally bursty, like the standing and sitting down. So these two types of stationary and non-stationary are going to be treated differently later. Obviously, if we look at the errors that are caused by different body movements, so the impact are different, depends on the magnitude, mostly the magnitude of the body movements. But we also look at how they get mixed up. So if we assume that the body movements and the vital signs mixed in the sense, in an additive sense, and if we also assume that they're independent, then if we use the ground truth or static sense, the vital signs sensed under static body to correlate with other signals under other body movements, they should still show high correlations because additivity and the independence will actually, under the correlation, other components will be mostly become zero. However, the reality doesn't show such a case. So this kind of proved that the mixture between, in our sensing space, the mixture of different body movements or body motions are highly nonlinear. So decomposing highly nonlinearly mixed signals are still a very difficult problem. However, we still have hopes. Firstly, we have different motion features. For example, let's say the stationarity, regularity against non-stationarity. And secondly, the vital signs will have very specific patterns. And last but not least, RF sensing, as we believe, offer fine granularity to sense all these differences. So in order to pick up the differences so that we can extract vital sign signals out of body movements, we are leveraging a novel deep learning method called contrastive learning. So the idea itself is not new. So I mean, human beings are using contrastive learning for thousands of years. Basically, what we're relying on is the difference or the similarities between different objects so that we can learn to classify them. For example, there's two images, or both for cats, but they're different images, not the same cat, but we still can observe similarities. Where these two are for cat and dog, and they are contrastive pairs, so that we can learn that these images are for different animals. So basically, we're just training the neural network to recognize the similarity and also recognize the difference. So this is the idea of contrastive. And for contrastive learning, data augmentation is very important and it's also a tricky aspect of this learning method, because if we don't do augmentation, we wouldn't have sufficient amount of data, and to generate especially this kind of contrastive pattern. So, for example, we can do different cropping, different rotation, and different shifting, so that we can have plentiful amount of images for the same cats and for the same type of image like for cats, and also for the contrast instance between birds, cats, and dogs. Okay, so if we want a full-fledged explanation for contrastive learning, it might take an hour. So we're just here using a very basic idea to do some illustration. For our method, for our problem, we can't use those image-based method because we get our time series data, but we still can learn from them to actually come up with, let's say, the so-called extended observation data sets for similarity, and contrastive instances for contrastive learning. So suppose we have this sensing matrix, then that is showing on top left corner different signal strings. And then for extended observation, we simply just do time shift. So this actually shows the correlation in time. So And for the contrastive instance, the beginning is still the original data matrix. And then for the contrastive part, we'll actually put the time permutation so that if we look at the marginal distribution in terms of data, they're still the same because this permutation doesn't change the data. But if we look at the temporal correlations, they're totally annihilated. So this generates contrastive instances to compare with the original extended observations. So we are training a multi-layer perceptron to be as a classifier so that we can distinguish between this, samples from either the extended observation or the contrastive instances. So the idea is that if we can successfully discriminate any samples randomly pick up out of each of these data sets, and in the feature space, we'll be able to separate the different body motions. So we're not presenting the theoretical proof here. So yeah, interested audience can find it in one of our references. And so this slide is for stationary body movements, which involves a temporal permutation. But if we have non-stationary body movements, we don't need to do permutation anymore because the non-stationarity itself will create contrastive instances, so that we just need to chop the data sequences into different segments. And then we try to randomly pick up examples or samples from different segments and use the MLP to classify them back to the correct segments. Again, the same principle applies. So if we can successfully discriminate each sample from which segment, then the underlying feature space will have, the decomposed motions, including two vital signs. So last but not least, we need, because the results of decomposition were still pretty rough, we need to smooth them. We also need to concatenate the different sliding windows together to generate continuous monitoring results. For this, we use an encoder-decoder network assisted by a discriminator driven by ground truth, so that we use the ground truth kind of denoise the signal and also provide kind of background information to concatenate or merge different segments together. So that's the technical explanation, and then now comes the experiment evaluations. So we first showed that if without the encoder-decoder, the signal is still very, promising, but contains a lot of noises. So this shows that we do need the encoder-decoder to do the smoothing. But on the other side, it also shows that we're not using ED to overfit the signal, so that we simply generate results out of the ground truth. So we also choose a baseline for comparison, although, as we said earlier, we are the first to work on this, body motion robust vital sign monitoring, full-fledged manner. There is no direct comparable examples before, but we still take most recent work from last MobiCom, which didn't consider motion robustness, but it's the most recent proposal in the same research line. So although that paper was considering recovering SCG, but we realized that on the body movements, SCG is so weak that we can't recover it. So we're shifting our direction to the blood pressure. Although blood pressure waveform is much simpler than the SCG, but it has a much stronger signal-noise ratio. So we can sense it. Basically, with the kind of illustrative results we're showing here, that after the full pipeline as we showed before, so our recovery results in terms of different motion types, and so our results are very similar to the ground truth, and which is much better than baseline. So some detailed investigations are here. So we have investigations for, well, I think the time is going pretty fast. Let me just skip through most of these results. You can still read the papers. So we look at different metrics and different features within the heartbeat. And we also look at whether we can do cross-technology transfer, from the IRUWB radar to other FMCW radars, and also look at whether the antenna diversity would help to push the results better. So finally, we just claim that yes, we can do motion robust vital sign monitoring. And this are not just a paper, we actually have products related to it. So if you're interested, you can access our company that is selling this product. Thank you.